It features a custom 3D printed oxygen life support system and a watertight seal, all integrated into a streamlined, low-profile frame. But this gear isn't for a human diver. It is scaled to the millimeter, engineered specifically to fit onto the back of an insect. The Madagascar hissing cockroach serves as the biological chassis for this technology, chosen for its durability and specific physical dimensions. Engineers at Nanyang Technological University in Singapore developed its prototype within their campus labs. The project targets a lethal engineering bottleneck in search and rescue, where current technology fails to penetrate the most dangerous environments. Heavy urban flooding, like the kind recently seen in Myanmar, turns city infrastructure into a series of inaccessible, high-stakes puzzles. A collapsed building submerged in water presents zero visibility, shifting debris, and structural fissures far too small for a human, or even a dog, to enter. This chart compares the energy required to move mechanical legs against the storage limits of a battery small enough to fit on a micro-robot. At this scale, the energy needed for propulsion consumes the entire power supply in minutes. Beyond power limits, rigid mechanical components like wheels or treads struggle with the geometry of rubble. They frequently become wedged in jagged crevices, leaving the robot immobilized. Because mechanical systems hit a strict physical wall in these conditions, engineers turned to a vehicle that arrives with its own native, pre-existing navigation programming. A cockroach possesses millions of years of evolutionary optimization for movement in tight spaces. It is a ready-made hardware chassis designed specifically for complex terrain. Their bodies are composed of flexible, overlapping plates. This allows the insect to compress its entire exoskeleton, passing through microfissures without damaging internal organs. The Madagascar hissing roach can also carry significant weight relative to its size, allowing it to transport digital hardware that would ground other insects. To steer the chassis, engineers interface electrodes with the insect's antenna nerves. By sending small electrical impulses, the system tricks the roach into believing it has encountered an obstacle, forcing it to turn left or right on command. Nature has already perfected the legs and the terrain mapping sensors. The engineering challenge is simply taking over the steering. Despite its resilience on land, the cockroach cannot naturally survive the flooded environments found in a disaster zone. Submerged, it will drown within minutes. This 3D printed suit is designed to provide the insect with an aquatic operational window. The gear is custom molded to fit the specific curvature of the roach's body. The suit creates a watertight seal over the insect's back. This protects the digital control link from moisture, preventing a short circuit while fully submerged. This timeline shows the impact of the chemical oxygen system. It provides enough life support for the Cyborg to remain active underwater for 180 minutes, a massive increase over the 10-minute battery life typical of mechanical microdrones. By letting the insect provide the energy for movement, the NTU team successfully bypassed the battery limitations that stop traditional drones from entering these zones. Controlled tests in a university pool are one thing, but a real-world disaster site introduces factors that are difficult to simulate. Signal attenuation is a major hurdle. Digital control frequencies struggle to penetrate layers of dense, wet concrete and water, which can cause the link to the insect to degrade or drop entirely. The strength of aquatic currents also poses a threat. In a flooded building, rushing water can easily overpower the physical strength of the insect, pushing it away from its target area. A field deployment would likely involve a swarm of these units. By releasing dozens at once, rescue teams can increase the chances that at least some units will find a way through the debris. As the insects explore, their telemetry is sent back to a central hub. This data allows engineers to aggregate their paths and create a 3D map of the interior, pinpointing the location of survivors. When people are trapped beneath tons of flooded rubble, we face a choice between waiting for robotic technology to improve or adapting the biology that is already capable of the job. Whether hacking an organism is an ethical compromise or an engineering necessity is a question that will likely be decided by the first lives these cyborgs help save.